Everyone have this slide, everyone like it. Me too, of course. I will work on two packages. The first one about improvement and measurement tools, and the second one about advanced characterization of raw material, refractories and joints. About the first one, I know that the purpose of these packages is to improve the existing methodology and or develop new methodologies. In my case, about the thermal instrumentation for temperature up to 1500 degrees, maybe. And this technology will be used for laboratory scales, but also for industrial application, with the help of thermocouples and thermovisual cameras. This is what planet. And another task is dedicated to the development of devices for thermophysical property characterization, depending on the testing method, and also about the kind of refractory that we will study. About the second packages, the purpose is to create a database, a huge database about material properties. And one task is dedicated to the study of the microstructure and its evolution. I mean, consider different situations, corrosion, high temperature, different raw material, and so on. And to better understand the relationship between microstructure and thermomechanical properties. We know that there is a strong relationship between them, but we want to better understand this relationship, considering the influence of solid phases, porosities, and interfaces. As we have we have different information about the influence of solid phases and porosity, particular attention will be put on the role of the interfaces at the microscale level as grain boundaries, but also at the microscale level as joints. Two kinds of material will be used, industrial material of course, but also simplified model materials that can be useful to have a first understanding of the relationship between microstructure and thermomechanical properties. But not just to understand this relationship, but of course also to evaluate the thermal properties in a range between 20 degrees to up to 1500 degrees. And these thermal properties are heat capacity, thermal diffusivity, and thermal conductivity, that are really important for all ceramics in peak resistance for thermal stresses and to determine operating temperature and temperature gradients. For this task, I will use different methods, for instance, the laser flash method, but also hot wire method, and hot disk method, and probably also other methods. We will see. And I already started to familiarize with the laser flash method on simplified model materials. For instance, there is these two materials, silicon carbide and zirconia. This is a classical thermogram of laser flash method. These two materials were chosen to show the difference in thermal conductivity from an insulating material and a semiconductor material. And so the influence of atomic bonds and also the structure. For the same principle, almost, I make some experiment on the aluminum and sapphire, in this case to show the influence of porosity and also grain boundaries that reduce the thermal conductivity because they make phonon scattering, so reducing in-free paths, so the thermal conductivity. And in addition to all this information, we are also planning to consider the influence of anisotropy, the influence of high temperature behavior in terms of radiation and gas conduction, that became really important at temperature, and also the material with evolving microstructure, different phases, different properties, different problems. Okay? And I think that in this project, the most beautiful aspect is not only the relationship between students with industrial and with the university, but also the interaction between each ESR. For instance, all this knowledge became data for work package 3, that is not my packages, but they should create about my data and other. Design new thermal insulating material by numerical modeling. And then we can also use all this information to improve tools for in situ measurement temperature measurement. So, okay, that's it. Sure.
No, thank you. Any questions?